Hello everyone. I don't think you guys can see me. I think I had to fix something real quick. Always with the technology. Oh, I still don't think it's working. We'll go ahead and get started here in a sec. I don't know why my webcam isn't working. I'm gonna just see if I can get it, if I can troubleshoot it really quickly. It was literally working like 30 seconds ago when I was gonna start this, and it just like randomly turned off. Don't know if my webcam broke or something, but I think I might be without webcam today. I'll probably get it fixed by next time, but I think it just broke. So I'm gonna just go ahead and dive in, and I apologize that you can't see me, but hopefully you'll still be able to understand everything that we're gonna go over about physics, since that does not require my face. So we're gonna talk about forces as well as torque. You have any questions, or you're a little bit like lost about what I am saying, always feel free to go ahead and pop some comment in the chat, and I'll try and get around to them and answer them to the best of my ability. This will build off of the last live that I did, but you don't need to have seen that particular live to still understand what it is that I'm going to talk about today. So if you didn't watch the ones on kinematics last week, it's going to be totally fine. We'll go ahead and just dive right in. And start off, I'm just going to go ahead and define what a force is. So a force is a push or a pull. Basically, if you think about all the variety of different sort of like force is, you can, at the end of the day, just put them down into these two different terms. And I think it's just really nice to have simplistic ways of viewing the different basically terms. Yes, this will be recorded, and you said that there is an echo. Not sure why there is an echo. If it keeps happening, let me know. I can try and mess around with it. My webcam did just like break at the beginning of this, so today, apparently having tech problems for some reason. When we think about, forces, we're talking about these sort of like pushes or pulls. And with the pushes or pulls, we can also think about things in terms of them being vectors. So that just means that these things have direction as well as the size. So if we're sort of thinking about the three different boxes that we have here, we can think about, okay, right, like maybe this one is going to go up, and it's going to be relatively large. This middle one will be up, but relatively small. And then this last one will be down. So we're sort of seeing the magnitude. That's going to be the fact that these are different sizes, just getting at that idea from like the vectors lecture from last time about magnitude. And then we also are seeing we're also seeing direction differences. So this one in the middle, up, and this guy over here is down. Pretty straightforward. The way this is going to work is that since they're vectors, that means that they can go ahead and add. So if we have, two people, they're going to push on this box. They're going to push just as hard on this box. Then this box is not going to go anywhere. So if we wanted to represent it, we could say, okay, this was person number 1 pushing here, and then this was person number 2 pushing like this. These two cancel out. The box doesn't go anywhere, just because two vectors that would cancel each other out would do this, and forces are vectors. Alternatively, we could have two people that are going to push on the same side of a box, And if this happened here, then what we would see is that these would add up, and now this box would actually move and it would get shoved to the right. So now we would see this moving over here. And again, it's just because it's vectors. And so if we wanted to look at it this way, we could think about maybe putting some numbers to it this time if it's going to end up being additive. So in this case, if both people were pushing equally as hard, say that one was using a push of 5 and the other person was using a push of 5, then we could say that the net, or the overall, or the total, would end up being a push of 10, because these two will add up. And I know a lot of this is like super, super basic right now, and the whole reason for sort of starting at this level is because realistically, all force questions are going to come down to these really basic ideas of what is going on. And so what I've been talking about with these sort of additive pieces is what we call a net force. And it's really net force that matters when we're thinking about what is going to happen with a object. So like when you go and you push on it, what you're going to see is a net force determining whether or not this thing is going somewhere or not. So if I go back to this one here, right, like because there was no net force because the two canceled, the box doesn't do anything. Whereas in this second circumstance, there was a net force, we were pushing to the right, and because we're pushing to the right, we're gonna get movement of this thing net to the right. So net force is what's gonna matter when it comes to whether or not our box does anything. Now, when we think about different forces, they can be caused by all different things, and we're gonna go over the different types of forces in a moment. But the first thing that I wanna kind of look at with this is, you know, like, how does this work out if we have a net force and then we have these three different components? Like, how do we actually use this information? So what we're going to do is we're going to zoom in to the box at the bottom of this sort of container of water. And what we're going to see is that there's going to be one force pushing up right here. There will be a second force pushing here. And then there will be one force coming down. We're not going to worry about what these different forces are right now. We're just going to sort of work with some overall concepts. And let's say that in this particular circumstance, there are no net forces. So there is no net, which basically just means this box is just going to sit here. It's not going to do anything. What does this mean? Well, if we think back to our box, this means that whatever sort of pushes that we had, they have to all equal up to one another. So if we have 10 going down at the bottom, and this guy right here is 7 going up, then this one that is also kind of pushing this thing up would have to be 3. Because again, if there are no net forces, this thing is not moving anywhere, then what we know is that all of these things must cancel out and lead to this particular scenario. So in this case, the 3 plus 7 must be equal to the 10. That way we have 10 going up, 10 going down, and all of these things cancel out. Now, this brings us to Newton's first law, which this to me looks like a ginormous mound of cotton candy. It's supposed to be a artistic rock. We're gonna go with it's a giant mound of cotton candy. So if you have a giant mound of cotton candy and it's just sitting here and you don't do anything with it, you just leave it on the ground, it is going to stay here doing whatever it was. And that's essentially what Newton's first law says. It says that if you don't basically apply a net force, this thing is not going to do anything. So if I just keep staring at this mound of cotton candy, there will be no change in whatever it's doing. It's not going to move, it's not going to get pushed or pulled around or anything like that. Now, one of the ways that I think this can be a little bit confusing, right, is this idea of like, what if something is already in motion? So let's say that we have this car, and this car is traveling at a constant speed. Let's just say that it's going 40 meters per second. So it's just sort of chugging along, chugging along, chugging along at 40 meters per second, like normal. This thing is actually also not subject to any net forces. And this is because, remember, if we go back to Newton's law says whatever the thing is doing, it's going to keep doing that unless we put some sort of push or pull, some sort of net push or pull onto this thing. So if this thing was traveling at 40 meters per second, and it's just continuing to do that constantly without changing, it's not changing direction, it's not changing speed, there are no net forces. And the MCAT likes to ask questions where they'll sort of put this idea in of like, hey, you have a stationary box, or you have something that's at constant velocity, And then what we know is like, okay, so there are no net forces, and you need to be able to read into that, right? That constant velocity or the fact that the thing is stationary and use this. Is this ignoring friction so far? Yeah, we're not really thinking about friction. We'll talk about friction a little bit later, but currently we're kind of just ignoring friction altogether for the sake of just understanding some of these more basic concepts, and we're going to layer in more of the forces as we go and build up to what you would actually see on the MCAT. My reason for doing this is just that a lot of people lack some of the more like a basic understanding of what is going on in forces, and I think because of that, it actually makes the MCAT style problems much harder. If we understand this, the MCAT style problems actually aren't as hard as I think a lot of people think they are. Hopefully you'll come to see this as we get a little bit further in. Okay, and this can be applied to all kinds of different scenarios. So when we think about forces, right, we're not thinking about fluids yet. We're not thinking about, say, like if this was a positive charge, electrostatics, but force is a concept that's going to continually come up. It's going to come up in fluids, it's going to come up in magnetism, it's going to come up in electrostatics. So I want you to kind of have this idea that like all of the stuff that I'm talking about right now will continue to apply when you cover that material in the future. So if I'm talking about constant forces and I have, say, this, object and it's just suspended, it's not moving, right? It's in the middle of this fluid, then we can come here and say, okay, this is experiencing no net force because it's just stationary sitting there. And if this object is just hanging from some rope and it's not moving, it's not doing anything, we could say that there are also no net forces. And if this positive charge right over here was going at a constant velocity, then we would also say that this right here has no net forces. So in all case, right, like we have something in fluids, we have something just like straight up regular forces, we also have something that is in electrostatics. All of this sort of like no net forces stuff can be applied, and all of the things that we talk about will be continued to apply in the future as well. So this brings us to what types of forces do we have? We should sort of think about them, because when we want to start solving these problems, we're generally going to represent them in a forced body diagram. And the key to being able to solve something in terms of a forced body diagram is knowing what forces need to actually go down on your piece of paper. And this comes down to the scenarios because different types of forces just come from different types of scenarios. So if we understand the types of scenarios and the types of forces that go with them, you'll sort of always know what forces should go down on your piece of paper. So the first one is going to be gravity. This is pretty much going to be always, so long as we are actually like on Earth or some sort of planet. The way that gravity works is basically things with mass, they attract each other, and it doesn't really matter how big these things are. So if I had a ball here and another ball here, it turns out that these two things are actually trying to move towards one another. Kind of like in electrostatics, it's just that this is happening from a mass perspective. Now, in the context of gravity, in this particular case, it's just that the Earth is the most massive thing, so gravity is going to be tied mostly to Earth, because all of these little interactions, say between like, I don't know, like your pen and your hand, like the mass of those things is just so tiny in comparison to the Earth and your pen, or the Earth and your hand, that is going to be the force that wins, and we don't really care about all these little tiny ones that keep pulling together because the masses are just so tiny. And we can sort of see this when we look at the actual force of gravity between two different things, which is that the force of gravity will be equal to a constant g times m1, m2, so that's just the two masses over the r squared value. So basically just like some constant that helps us adjust for the fact that we are thinking about how masses attract, the mass of one thing, the mass of the other thing, as well as how far away they are. It's possible that you could be asked a question on this. We have not seen one on AMC material. I know that there are ones out there on other third-party resources. So this is going to be something I'm going to just kind of move on from because we just don't see it all that often. In terms of this is kind of our first one. And so if we happened to think about this apple here and it is on Earth and we wanted to represent gravity, I'd be like, cool, I'm going to just draw this down and that will be force of gravity. The next one is going to be a normal force. And the normal force is basically just how much some object sort of like smushes into a sort of like, surface. So if we think about this box, right? This box is sitting on a table. That means that it has a force of gravity. And if it is stationary, then this box should not be moving. It should not have a net force. which means that the gravity can't be the only thing that is present here. Because if gravity is the only thing that's present, this thing should push its way through the table, but it doesn't. And that's because we have normal forces. This is where a surface, whatever this thing is in contact with, basically pushes against and resists the push that it's getting from some particular object. And it doesn't matter the orientation of this thing. So in this case, I have it in a more like standard situation. It's pushing down on a table, but there's no reason that this can't happen with something like this over here. So let's just imagine that you are holding, let's see if I can actually draw a hand, you are holding this thing into the wall. So you have a force push into this. And again, assuming that you're not some like Hulk or Superman type of character, you're not going to just like punch this box through the wall. It's just going to say suspended right there, which means that this object is going to have a normal force out like this. And it's because it's coming from whatever object you're pushing into, it will be determined by how much you push into that particular object. So for example, if we think about a second object on this right here, and we know that this object would be pushing down with the force of gravity, but now let's imagine that we tie a rope to it and we pull up. That would be a tension force. We'll get to that in a little bit later, but we're going to pull up on this right here. Then what we're going to see is that the normal force is not going to be equal to the force of gravity. In the first situation, that's exactly what would happen. Normal will be equal to force of gravity because we know we have no net force in this situation, so the two things must be equivalent. But in this scenario, we have three forces, and if this thing is not moving, it's not going anywhere, then in this circumstance, the normal force and the force of tension, the force in this rope, would have to be equal to the force of gravity. And so here we can see that the only way for this to work is if the normal force is smaller than the overall force of gravity, because it is only one component of it. So you can't always assume, and I think some people will sort of make this assumption, that like, oh, my normal force and my force of gravity are always the same, and that won't always be the case. Normal force is also what we call weight, and that's because when we think about weighing something, we can think about a scale, and we're basically saying how hard do you push into a scale? Well, how hard you push into something is just dictated by a normal force, so when we talk about weight, we're usually talking about what a normal force would end up reading. And I want to just sort of pepper in one concept here, which is what is a normal? Because you're, again, going to see this concept in the future, and so it's much easier if we understand the general concept of this when it comes up, say, in optics. Normal is really just sort of saying like, hey, you have some sort of surface, whatever the orientation of this particular surface, we're going to think about something that is 90 degrees or perpendicular to that. So we saw this very clearly when we had our table. Our table was just sort of sitting here, and then if we wanted to think about a normal, I would just come and draw something that is 90 degrees to this. And we saw it when we looked at the wall as well. Our wall was like this, and again, we would think about something that is perpendicular or 90 degrees to this. When we look at inclined planes, we can think about the same thing, and if we want to think about our normal, we will come and we will draw something that is 90 degrees to this particular surface, like this here. When we think about Snell's law later in optics, if we have some sort of thing and the light is going to come in, we define a normal, and that normal is simply 90 degrees to whatever surface we care about. So if the light is coming in, we can look at its angle to that normal. So hopefully you see, like, normal is just a general concept, and it's really just the same thing. It's just it looks a little bit different in terms of the orientation of the surface that you're pushing into. All right. Our next one is going to be the buoyant force, and this is simply because you have some sort of fluid at play. Now here I've obviously drawn what we think of when we think of fluids, which would end up being a liquid, like water or something along those lines, but it can also be a gas. So fluids are not just going to be liquids, they are also gases, which is why if we want to think about the forces on a balloon, which is in air, we can also think of this as having a buoyant force, even though the balloon is not in contact with any sort of liquid. This is always going to be forcing something up. So for example, if we look at this object here, the buoyant force would be pushing it up like this, which when we looked at the other scenario and we were saying this thing was on the bottom, that's what we were looking at. And two, in this scenario, because it's sitting on the bottom here, right, on the bottom of this particular glass, we also know that it would be having a normal force. So when I used that scenario before and I didn't actually label these things, now you're seeing a little bit more clearly what forces I was actually talking about. The last one, which is pointing down, was the force of gravity. So when I said this object was stationary and just sitting here, you can now see the different forces that was making that up when I set those things equal to each other. The same thing would be true with the balloon as well. There is gravity acting on this. In this case, it is not in contact with a surface, so we won't have a normal, but the buoyant force of the gas will be pushing this up. And it would depend on whether there's a net force or not, depending on if this thing is having a greater force up or a lesser force down or whatever happens to be going on. The last one, or maybe not the last one, but the next one is going to be tension. Tension basically happens anytime we have some sort of rope or other kind of like string-like surface. I mean, even our arms, if you want to think of our arms as like little rope arms, it's another way that you could kind of look at it. And basically, these things are going to be holding it up. To me, it's kind of like a normal force, sort of, but it's like happening in a rope. I don't know if that makes a ton of sense. Hopefully, as I explain this a little bit more, it will be a little bit clearer. So for example, this box that's hanging right here, the force of gravity says that it should fall down, but it's not falling down, it's just sticking there, which means that we know that there must be some force holding this up, and in this case, this is the tension force. It's kind of similar to the normal, right? Because the normal was keeping this thing from just falling to the ground or falling through the table. Here, a rope is causing that to occur. Or, in this scenario over here, you can imagine that in this circumstance, what we're going to see is that you have a force of tension pulling on this particular object at this angle. We'll get to angles in a sec, but that's essentially what we're seeing. And then we also have the electrostatic force. This is going to be a lot more similar to the gravitational force than a lot of people realize, and basically it's just where positively charged things will go ahead and attract, negatively charged things will repel, positively charged things will repel other positively charged things, basically opposites attract, and then like will go ahead and come together. It's most similar to gravity, because if we look at the equation for this, so this would be the electrostatic force, is equal to some constant k, q, so we're looking at charge this time, q2 over r squared. Really, really similar. It's just that instead of dealing with gravity as a concept, it deals with charge attraction as a concept. So instead of mass attraction, charge attraction. Lots of similarity with these guys here. And you will have this at play when you have charges at play. We also have the magnetic force, which would obviously involve magnets, and that's really all I'll say. And then we also have friction, and we're going to dive into friction in a lot more detail in a moment, because there is a lot more to kind of dive into it. But you want to know that friction will be at play when the MCAT doesn't tell you, like, hey, don't care about friction, because they're going to do that. They're going to say, like, friction doesn't matter a lot, and that's just because friction, when it's there, can make questions a lot more complicated. And so because of the fact that the MCAT is trying to put something at a level that is reasonable on test day, right? Like you have to actually be able to do this math, and you have to be able to solve this problem and not have it take 5 minutes or whatever unrealistic thing. They will often exclude friction. But if they don't exclude friction, they don't tell you that it's there. If your object either has movement, so it's moving, this, in this case, we can say that its movement would be in this direction here. Friction will always work to oppose movement, like this. But it can also act on a stationary thing as well. So if I had a box and it was just sitting here, and this thing was completely stationary, but you were pushing on it, right? You're putting a little push, but it's not moving. It can also oppose what I would say is supposed movement, or like if friction wasn't there, would this thing move? And if it did move, where would it go? So in this case, right, this thing would move to the right. Obviously, it's not moving to the right, so there must be something stopping it from doing that. And so what we'll see is that we have a force of friction coming over here like this. I realize it's getting a little bit cut off. I'm gonna go fix that really quick. Okay, that should be perfect. Now you should be able to see everything again. So now what I'm gonna go ahead and do is just recap the different types, so that way we can understand a little bit more clearly what we have in terms of all of the different ones that we've gone through, because I did just discuss quite a lot. Okay, so first one, gravity. And when are we going to have gravity if we're thinking about trying to draw some sort of object? Pretty much always. So long as we are not in the vacuum of space and masses that are around us are way too far away for these to actually be attracted. So that's going to be number one. And then we have normal. So when will we need to involve normal forces? Well, we're going to involve normal forces anytime we are in contact with some sort of surface. And remember, it doesn't really matter on the orientation of that surface. The surface could be like this, the surface could be at an angle, the surface could be straight up and down. So long as something is getting pushed into a surface, there will be a normal force. Next, we have the buoyant force. This will occur anytime you have a fluid. There are two fluids that we should be thinking about, right? That's going to be gases, a little bit less common, and then we also have liquids. So we saw that example with the balloon, and we also saw the example with the block in the water. The other thing that we will have is going to be tension. And for tension, that's going to be anytime we're involving a rope. This could also be our arm if we are hanging off of something like this. If I'm hanging off of a bar, there would be tension holding me up to that bar. We also have the electrostatic force. And this is going to be at play anytime we are dealing with positive and negative charges. So remember, all of this is just sort of like, you know the scenario, you know what forces you need to put on your force body diagram because they just tie directly into the scenario. You have the magnetic force. That one I think is going to be a little bit more obvious. You have a magnet involved, or a magnetic field. And then lastly, we have friction, which we need to dive into a little bit deeper here in a moment. And with this one, right, this is going to be anytime you have supposed or actual motion. Thank you, Ibrahim. Trying to make more videos. I know there weren't a ton out. I'm super glad that you're done with your MCAT, and hopefully it went well. So here we have kind of our force recap in terms of what we're looking at. So far, what we've talked about for the most part is just like the different forces, but we haven't talked about how forces work outside of like there are net ones. So we're gonna look at that next. We're gonna say like, okay, yes, F equals ma. Why does it equal that? What is it telling us? But let's go ahead and think about creating a scenario where we're gonna have as many of these things as possible, or even like all of these things in one scenario. So let's go ahead and think about this. Let's say that we have a glass, and this glass is going to be filled with some liquid. And in here, we have sitting on the bottom a cube, and this cube is going to be tied to a rope like this here. And this cube is going to be metal, and there's a magnet over here on this side attracting it this direction, and it is also positively charged, and so we have a negatively charged thing over here. So if we're looking at all of these things, let's start to put all of them on here for a moment. The only thing we're not going to get in here is friction. So we know going down, we have the force of gravity. And pulling up, because we have a rope, we have a force of tension. And because we have a liquid, we have a force of buoyancy. And because this object is sitting on a surface, we have a normal force pushing up. And because this thing is charged and there are charges near it, it's going to get pulled this direction over here by the electrostatic force, which we'll just go ahead and call Fe. And because there's a magnet on the other side, and this thing is metal, it's going to get pulled to the left, and then we can come and say over here that we have F of B for the magnetic, not F of B, F of M, we'll just call it M here for a sec. So now you can see like how knowing all of these different scenarios helps you figure out how to actually draw a force body diagram, because drawing this sort of detailed force body diagram really just comes from knowing the different scenarios. So this is why we spent all that time going through the different forces. So now we need to think about, great, we know in what scenarios different forces are there, we sort of know how to draw them on there, but like how do we actually quantify them? Like what do we see? And this is going to come down to understanding what forces actually are and what they do. So we know originally they're pushes and pulls. So what is a push or a pull going to do? Well, first it's going to act on a mass. So we can think about three different objects. So at the top we have a ping pong ball, and this has the least mass. And then we have a tennis ball in the middle, and this has a moderate amount of mass. And then lastly, we have a bowling ball, which has a lot of mass. And let's imagine in each scenario, you're going to take a paddle. Let's just say it's a ping pong paddle, and you're going to come and you're going to smack each one of these things. We're going to think about what's going to happen. You're going to smack it just as hard every single time. So you come and you smack the ping pong ball, and if you predicted that the ping pong ball will go flying, That would be correct. That would make sense. Now you're going to take your ping pong paddle and you're going to smack the tennis ball, again, equally as hard, and it will come and it won't go quite as far. And then lastly, you're going to take your ping pong paddle and you're going to smack the bowling ball here. And what's going to happen to the bowling ball? Well, the bowling ball is just going to sort of like along, right? It's just going to peter along. Maybe it won't really go anywhere at all. So what we're seeing in this particular circumstance is that as we increase the mass of our object, the way that the force interacts with this, assuming that we have the same force, is that it will not speed up or slow down. It will not move as far, or it will not move as quickly. Now, let's go ahead and think about this scenario here. So in this circumstance, what we have is we have three different options. We're going to change our forces now. So instead of thinking in terms of the size, we're going to think in terms of augmenting the actual force. So we're going to imagine a little small tap. So let's say that we're hitting a ping pong ball in each circumstance. So in this first one, we come along and we just, the ping pong ball just barely, just a little tiny tap. Or we give it an average whack. Or we give it a really big smack. We're going to just come in, we're going to just smash on this ping pong ball. Well, what would we expect to have happen in this circumstance? Well, we should imagine that the small tap, the ping pong ball is going to go not very far. And if we give it an average whack, it's going to probably go further and faster. And if we give it a really big smack, this thing is just going to go absolutely flying. And that's exactly what we should predict in each of these cases, which is if we chart out the relationships of what we have so far in terms of the actual equation, right? F is equal to ma, which is what Newton's second law says, is that when we push and pull on masses, net push and pull on masses, they will accelerate. That is to say, they will change speed. They will speed up, they will slow down. And so what we're going to see in these circumstances here is that as you increase your force, you are going to have greater accelerations. Because we know that the harder you smack something, the more it's going to speed up or slow down. And we also know that the more mass that you have, the same force is not going to be able to cause this thing to speed up or slow down quite as much. And so in this case, we would see that the acceleration would be lower. So all of these sort of combine to describe what we have going on. This first relationship here, we call inertia. Inertia is just this idea that like when something is in motion, it will stay in motion. You might say, how the heck does that have to do with mass and acceleration? Well, you can see that things with greater mass are not going to change their acceleration as much. So something with more mass will keep doing whatever it was doing to a greater degree. So for example, if you have a car and you have a mosquito and the two collide, the car is probably just going to keep going along doing whatever it was doing because it is much, much greater in mass than that poor little crushed mosquito. Well, maybe I don't feel so bad because it's a mosquito. It's probably going to kind of hit the windshield and it's going to get carried away. And this is that concept of inertia, right? And that's kind of what we are seeing with this second law. So how do we begin to put some of these particular concepts together, right? We have the first law, which is this idea that things aren't going to really do anything unless we actually go and push on them. And now we have the second piece, which is that force is equal to mass times acceleration, and we've seen the different elements of what is going on. So let's say in this case, what we want to find out is what is the normal force? So we have a question and it asks like, hey, what is the normal force in this circumstance? So step number one, we want to represent the forces that are at play and think about whether or not this object is moving or not moving. Will there be net forces or will there not be net forces? So right here, it's just sitting there. It's a block that's sitting there. There are no net forces. So we know that gravity will always be extant, right? We're on Earth. We're going to assume we're on Earth. And this thing is sitting on a surface. I don't know what the surface is. Maybe it's the ground. Which means that we have a normal force. Because it is stationary, these two things are just canceling each other out, which tells us that the force of gravity must be equal to the normal force. And we know that force is equal to mass times acceleration. So we say that the normal force is equal to mass times acceleration. We could also say that the force of gravity is equal to mass times acceleration, and that's the easier thing to do here. So ma will be equal to the normal force. We have the mass, that's just 5, and for gravity, you're going to want to know that this acceleration for the MCAT will be equal to 10 meters per second squared. So we have 5 kilograms times 10 meters per second squared, will be equal to 50, and when we multiply these things together, we get newtons, and that is the unit of force. It is a kilogram meter per second squared, so we know that the normal force in this circumstance will be equal to 50 newtons, since it is equal to the force of gravity. So this is obviously a very simplistic question. Let's go ahead and look at a slightly different concept, or a slightly different version of this particular one here. So let's say that in this case, what we have is we have some sort of positive charge. This guy is sitting right here, and it is going to weigh 0.5 kilograms. And it is getting attracted towards this guy here. It started at rest. So at rest, it was at 0 meters per second. And right here, 0.1 seconds later, it is now going to be going 30 meters per second, like this here. And here's what our question is. What force did this generate, or what force was present between these two objects in order for this circumstance to occur? Okay, so let's go ahead and think about what we have in this particular circumstance. So this object is moving, and it is not moving at constant velocity because it started at 0 and it is now at 30. So we have some sort of change in velocity that tells us that we have a net force, and it is moving to the right, so there must be some sort of net force coming in this direction. Presumably it's an electrostatic force. We don't have any information about the charges here, so we probably shouldn't be thinking about electrostatic stuff in this moment. But we know that any force, regardless of where it comes from, will be equal to the mass times the acceleration. Okay, well the mass component is relatively easy. We have that. That is going to be 0.5 kilograms. What about acceleration? This is a little bit harder than we had before. Before, when we had gravity, we just sort of like plopped the number in because we were given it. In this circumstance, we're going to have to figure it out. And this goes back to a little bit of our kinematics. So now we're combining kinematics with forces. And when we do this, right, we should know that acceleration will be equal to the change in velocity over the change in time. So how much did our velocity change? Well, if we look at this here, we can see that it went from 0 to 30. So it had a change in velocity of 30 meters per second. So we have that. So 30 meters per second. And how long did this take, or how much time changed or passed as we went from 0 to 30? Well, 0.1 seconds. Go ahead and just move all of my seconds on the bottom, make this a little bit cleaner. Times seconds, there's that meters per second there, and then it's being divided by the second. This guy will end up being 300 meters per second squared, which is an acceleration, which is what we were expecting. How did I get this? Well, what I did is I basically just moved this guy over to be 1, which means I need to do the same thing to the top, otherwise I'm going to change the number. So that's how I get 300. And then now we can plug this in. We have 300 meters per second squared. So the force will be equal to 0.5 times 300, or 150 newtons. So to get this thing to go from 0 to 30 in 0.1 seconds, there must have been a 150 Newton force between these two charges. Okay, let's go ahead and look at this next question. So this next one is now going to address a magnetic force. And again, we don't know anything about magnets, so we're not going to worry about this. So in this circumstance, what we're going to have is that this magnet is going to be generating a constant force. Say that in each circumstance, it's going to end up being 20 newtons. But in this case, what we're going to see is that this will have an acceleration of 10 meters per second squared, and this one right here will have an acceleration that is equal to 5 meters per second squared. So we know that these things are accelerating. That suggests a net force. Because there is a net force, we know that there would be an acceleration, so this force is actually doing something, which kind of makes sense. And now what we want to find out is going to be what is the ratio of mass 1, so that's going to be mass 1, to mass 2. So the ratio of mass 1 to mass 2. So in order to figure out the ratio between these two things, we're going to have to figure out what the mass is in either of these two circumstances and then work out the ratio. But before we do this, we can make some really good predictions about what we would expect based off of what we know. So we know that both are subject to the exact same force. If both are subject to the exact same force and one accelerates more, we know that it must have been the lighter object. Because if we go back to our scenario of the ping pong paddle and the ping pong ball and the tennis ball and the bowling ball, right? When we came in and we use the exact same force and we smack the ping pong ball, it goes flying. So it goes really fast. So this guy is fast. And it is going to be low mass, like the ping pong ball. But in the second scenario, we come in and we smack it and it doesn't go quite as fast, right? And we can see that this is going to be going slower than the first scenario. And that must tell us that we have a higher mass, which is similar to when we smacked the bowling ball in this circumstance. So already, if we had some answer choices, we would be able to eliminate some, because if we think about the masses, mass 1 will be lower. So when we look at this ratio, we should have a low or a small number to a big or a high number. So any answer choice that was saying me like 2 to 1 would be out, because that wouldn't make any sense. But answer choices like 1 to 2 or 1 to 3, those would be fine. Similarly, an answer like 3 to 1 would also be problematic for this one. So if you're maybe short on time, you can see how you can conceptually get a little bit further on a question like this. Or alternatively, if you're, having to make a guess because you can't figure out exactly how you're supposed to solve it, you can use these kind of concepts to get at least to this point, to get a little bit further in to solving this problem. So let's go ahead and find the masses of these things. So we know that F is equal to ma. So in the first one, the force is 20, and the mass here is what we're solving for, and the acceleration is 10. So if I just divide off 10, I will get 2. So the mass is 2. So let's just go in and label this. Low mass is equal to 2 kilograms. So now let's go ahead and come down to our bowling ball. And again, we're going to do this exact same thing. So in this case here, F is equal to ma. So F is equal to ma. So the force, that is going to be 20 newtons. Mass is what we're solving for. The acceleration in this case is 5. So we will come here. We are going to go ahead and divide off by 5. And in this case, we will get 20 divided by 5, or 4. So here we can come in and we can say that this will be a 4 kilogram mass. So if I wanted to sort of put these two together, I would say that my first one would be 2. So I would say this would be 2 kilograms, and that would be for any of these situations. And this would be 4 kilograms, which is a 1 to 2 ratio like this here. But here's the thing, there was a better way of solving this. We could have actually solved this without needing to do all of this extra work, find two masses, because they're all just proportional. So if we look at what we had, so if I just come in here, let's get another one of these guys here, right? We had 20 newtons. We had that the acceleration in the top scenario will be 10 meters per second squared. And we have that the acceleration in the bottom scenario will be 5 meters per second squared. And we know that as our force is constant and our mass increases, our acceleration will come down. We already used these ratios to figure out that we should have 1, right? The ratio of these things of 1 to 2 should go small to big. So if I look at these accelerations right here and here, what I can do is I can figure out, because there's no squares, because there's no other weird things, that it will be proportional to the ratio between these. So what is the ratio between these two? Well, let's just pick one. It doesn't really matter. Like, let's just pick one to put first. So let's say I put 10 to 5, which I would come in and say that this is 2 to 1. But because conceptually I know that that is wrong, then I'm like, oh, great, right? Like, really, the 1 should have been here and the 2 should have been here, and you can pick your answer on the basis of this. Now, why is this wrong? Like, why is it that when I just put 10 and 5 in this particular order, is it wrong? Well, because they're inversely related. So realistically, I shouldn't have put 10 and 5. I should have put 1 over 10 and 1 over 5, and I would have gotten the correct ratio. I would have gotten 1 to 2, but that math is harder, and I don't really want to have to do it, so I'll just use my concept to rearrange what I previously had, because that's just easier for me. And there's not a right or wrong. Like, you can solve this conceptually, or you can solve it the other way. Like, when you go and you look back and the other way that I solved it, finding the actual masses, either will work. But this is sort of starting to help you understand some of the more conceptual ways of tackling these problems that look a lot harder than they actually are. Awesome. So let's go ahead and look at our next scenario. So let's say that we have this ball and it has movement. It's going to be moving in the right direction here. And what we're going to see in this case is that this ball is being pushed this direction, it's being pushed this direction with a 10 Newton force. It is also getting pushed in this direction with an 8 Newton force. And let's say that it is flying through the air. And so because it is flying through the air, there's a little bit of air resistance, which is pushing against its movement. Air resistance is very similar to friction, it's just in the air, with a total of 5 newtons right here. And what we want to know is, what will this thing's acceleration be? So what is the acceleration of this? And it is a 1 kilogram ball. Well, they're already sort of telling us that there is an acceleration, which we should know hopefully by now, that there is a net force. Since we have a net force, we should figure out what it is. So just sort of looking at this, sort of as it is, to me I'm like, well, just looking at this, there's a lot more pushing it to the right. So I know, kind of just from doing nothing other than glancing at this, that I will have a F net in this direction. We can use vectors to figure this out. So I know I will have 10 plus 8, that's a total of 18, and then that will be counteracted by 5. So we have 18 adding up minus 5 for a total of 13 newtons. Hopefully I've done this math right. And then from there we can just plug this into F equals ma. So F is equal to ma. The F is 13. The mass is 1. The acceleration, therefore, will also be 13. So the acceleration is 13 meters per second squared. So again, just putting together some more of these concepts, showing you how to solve lots of different problems in lots of different varieties or different ways. One of the main things that the MCAT does is it just keeps changing the problem. They just don't ask it in the exact same way. They sort of ask it from this angle and that angle and this angle. So now we've seen a bunch of different angles. Awesome. So now, let's see. Yes, okay, here. So then what is going to happen when we are working at an angle? So now we're looking at this here, and we have this, and here, let's say that we're pulling on this box, like this. And this particular box is moving at a constant velocity. And let's say that this pull, like this right here, this is a 20 Newton pull. And from a horizontal, if we were to measure it like this would be at a 60-degree angle like this here. And what we want to know is, what is the magnitude of the force of friction? So the force of friction is our question here. So let's go ahead and think about breaking this down. So we know from just looking at this scenario right here that presumably we're on Earth, so we have gravity holding it down. So we can put in gravity, and it's on a surface, so there must be a normal, so the normal is up. And we're pulling on this, we're going to get to the pull in a sec. And then we also know that this thing is moving constant velocity, presumably to the right, because that's where this thing would move, is where we're pulling it, which means the force of friction is going to oppose any movement to the right and come this direction here. Okay, so then if we want to kind of figure out what's going on with these angles, this whole thing is on a nice XY grid. Basically what we have is we have this beautiful XY grid. Everything is oriented on this XY grid except for this pesky tension force. If we want to take this and be able to reconcile it with everything else, we need to use our vector skills, and we need to break it into the X and Y components to orient it back on this grid, to make it so that it fits with what we're looking at. So if we want to do this, we need to think of this just like any other vector. So if this is 20 newtons, we know that it's going to have a component that pulls directly to the right. So there will be a force like this. And we can call this the force of tension X, because it's just basically the component of the tension that is pulling in the horizontal or the X direction. And then we know that there's also going to be a component that's going to add up to the 20 newtons like this here, and that's going to be the force of tension Y. And what I'm going to do is I'm going to just grab this guy, and I'm going to move it over so that it's lining up in the in the Y direction with how we would expect it to pull, something like this. But we know what we have really is we have this triangle that we have constructed. So we have that this is 20 newtons. We have the force of tension X component, and we have the force of tension Y component. And we know that the angle between these two sides right here is going to be 60 degrees. This right here is 90 degrees, and this right here is 30 degrees. And so if you've watched the kinematics ones where we did our sort of like detour into triangle geometry, this is a 30, 60, 90 triangle. And for a 30, 60, 90 triangle, it has some really nice features. This one across the 90, we call this guy 2x, which means that it's going to basically be 2 times the size of x. Well, whereas x is across from the 30, so this guy right here would be x, and then this y1 would be x square root 3. So if 2x is equal to 20, then x must be equal to 10 newtons, and so we know right here that this guy is equal to 10 newtons. Now we're actually done, and why are we done, right? We should wonder, why are we done? Well, because we know that this is going at constant velocity, which tells us that there are no net forces. So we know that the force of friction, which is holding this thing back, and the force of tension in the x direction are exactly equal to one another. Well, we've already solved for the force of tension x. If we've already solved for the force of tension x, then we've technically already solved for the force of friction as well. Because there are no net forces, the two things cancel, and there we go. We've solved this problem. Now, before we move on, I want to go ahead and talk about one more concept here that we've technically already discussed, but it's going to be more important when we dive into friction a little bit deeper, and this is this idea of the normal force not always being equal to the force of gravity, and that's exactly what we're seeing here. Remember, it's how much this thing smushes into a particular object, right? So like the more that you smush into some surface, the higher your normal force, the more that that surface is going to push back up against you. Well, in this case here, right, the force of gravity is pushing down, but not all of that is going into smushing into the surface because we're pulling up, right? We're pulling this thing off the ground a little bit. So this normal force is actually going to be a little bit smaller than the force of gravity, because the force of tension y will make up the pull, right? It's going to make up the difference between these two. The fact that this is smaller. So that's where I was getting at with this. We'll see the full consequence of this in a second. Now let's look at a slightly more complicated question. And in this one, what we're going to do is we're going to try and find the forces in all of these different ropes in this case. So we have rope 1 right here. And we have rope 2 right here. And we have rope 3 right here. And we have rope 4. And we have rope 5. And all of these things are being held up. They're just statically hanging there. There is nothing that's like causing them to fall or sway or move at all. It looks really complicated, but it turns out that we can actually simplify this particular circumstance quite a bit. So first thing that we know is that if these things are just hanging there, there's no net forces. So whatever is holding all of this whole system up must also be whatever is pulling down on this entire system. So I want to just go ahead and zoom in to these first 2 ropes. So ropes 1 and 2. Well, the question is, what is it holding up? Well, it's holding all of this up. So the mass that each of these is holding up is going to be 20 plus 8 plus 2 plus 2. So that would end up being 32. So if I want, I can take what I had here and I can now simplify this problem into something that looks now like this. In this case, let's say that each of these will equally share any force. So how much of this force is coming down? Well, we know we have the force of gravity, and then we have 2 tension force. So we have force of tension 1, and we have force of tension 2. So force of gravity, that one's pretty easy, right? That's going to be m times g, so 32 times 10, for a total of 320 newtons. And then we know that it's being split equally among these two. So these will be equal, but we're just going to basically divide this guy in half. So half of 300 is 150. Half of 20 is 10. So this would be 160 newtons, and this will be the same, 160 newtons. Now let's shift our focus to the next scenario. Now we have rope 3 in the middle. And now we're going to think about, what is this holding up? It's holding up this right here. Because if you think about it, right, everything that is above it, it's not really holding any of that up. So the reality is that this can basically just turn back into a bar, right? All of that stuff is being stable, or is held stable. So now this is basically just hanging against some sort of fixed surface that's like nice and stable. So we can convert all of this in a similar fashion to an easier problem again. We have one rope hanging like this, and hanging off of it is all of this mass. So that's 8 plus 2, which is 10, plus another 2, which is 12. And here we're going to do the same thing. So the force of gravity is equal to 120 newtons, which means that whatever is holding this up, in case in this situation there's only one, which we define as the force of tension 3, will be equal to 120 newtons. And then when we shift and we go down here, we're only going to do one of them because they're basically the same. It's identical to what we just did. This becomes the new fixed thing. So now we look here, and we have 2 kg hanging down, which we do mg, same thing, ma. This will be Fg is equal to 20 newtons, which means the force of tension 4/5 will also be equal to 20 newtons. So it looked complicated, but we just broke it down into the different pieces, and we just converted it back into something that's much simpler. We're just really using all the same things that we've done before. My whole point with all of this was just to show you lots of different circumstances, so you can have a much clearer view of how the MCAT can vary the way that the question looks, but the actual solving technique ends up being essentially identical. Okay, awesome. So now I want to go ahead and move on. Where is it? Yeah, to friction. So what is friction, right? I've already sort of talked about how this is working, right? Like we know that it's going to oppose the sort of supposed motion, but why? Like why is it that when two objects sit on one another, they are going to have friction? Like when there is some sort of movement or some sort of push that would potentially cause things movement. Well, what we need to do is we need to zoom in depth and see what's actually happening between the two surfaces. So let's say we have this box, and if we zoomed in, what we'd see is that these objects, they are not perfectly flat. They have little bumps like this here. And what can occur is as these two objects attempt to move past one another, they can kind of get caught on each other. In addition to getting caught on each other, there's actually also going to be electrostatic interactions between these two things. So some partial positive charges on this one will attract to the partial negative charges on this one, and this holds them in place. And that is essentially what is resisting the motion. And why do we care, right? Like why have I spent all of this time talking about this right here? Because what this means is that the properties of the two specific things that are interacting are going to, in part, determine the frictional force. So it's not like frictional force is just going to be the same for every single thing that we're looking at, right? Like here, we're gonna have a maybe greater friction between two different objects simply because they are made out of different materials, but it's tied to the specific materials that they're made out of. So if you have one type of plastic interacting with wood, it doesn't really matter how much contact area there is between these two things. So long as you have that plastic and you have that wood, the type of electrostatic interactions and how those interactions are going to impact the frictional force are going to be the same. Like those two things will end up being the same. But we need to talk about two different types of friction because it's a little bit different. So we have static friction, and this is what we get when we push on an object that is static. It is not moving, and we're going to try and get it to move. And we also have kinetic friction, which is the friction when we already have an object that is moving. And what we're going to see here is that they are a little bit different. So when it comes to the static friction, what's going to happen is we're going to push on this object and it's going to basically oppose that motion, oppose that motion, oppose that motion. So right here, what we're seeing is we're seeing the force of friction kind of like as we push, harder, 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 harder. And at some point in time, there's going to be a moment where it breaks. And when it breaks, we're going to switch from static to kinetic, and it's going to look like this. So if I kind of came in here and I was just going to color code this and I give static yellow, what we would see is that this first portion right here, that would be yellow. And then if I come in and I give kinetic green, when it drops down, this right here, that is going to be your green kinetic friction. So a couple things that we should notice. One, static friction is not constant, and this makes sense. Let's say that right here, where it breaks, this takes 100 newtons for this to occur. So let's say that you have your box like this, and you're pushing on it, right? And you push with 100 newtons, and now this box is going to move. But prior to that, you were not pushing on this box with 100 newtons. Let's say that you were only pushing on it with 30 newtons. Does it make sense if you're pushing on it with 30 newtons, and the box is not moving, for the static friction to push back with 100 newtons? Well, no, because if that was the case, right, this is your force of push, and this is the force of friction. Friction should literally cause a box to move, but that doesn't make any sense, and that's not what happens, right? This is only going to oppose what you push into it up to a break point. So what we're seeing is that it's going up, 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 up as you push harder, 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 harder until it breaks. But kinetic friction is constant. So it doesn't really matter if this thing is going really, really fast or if it's going kind of slow. That kinetic friction is going to be basically identical across the entire line, which is why that thing ends up being straight across like this here. Now, like I was saying, you know, how do we think about these different factors? So we've looked at one factor, right? And we're going to come back around to it, whether this is static or kinetic, this will be true, was what type of materials that we have. So let's say we have three different materials. We have ice, we have asphalt, and we have some sort of maybe felt. So ice is really, really slick. So when we think back to those electrostatic interactions and the like little jagged bumps that these two things are going to have when interacting with each other, well, in this particular case, what we're going to see is that that is not really stopping the motion that much. And if we want to define or quantify this value, we're going to quantify it as a coefficient of friction. And this will come in two forms. You'll have a coefficient of static friction because, right, we know that there's a difference. So there must be different interactions between these two things. So you have the coefficient of static friction and you have the coefficient of kinetic friction. And in this circumstance here, we represent it by mu, it will be very low. Now when we come to asphalt, what we're going to see is that this is a much more like friction-y surface. So it's just going to resist movement a lot more. So it will have a very high coefficient of friction. And let's say the felt is a little bit more in the middle. So here, we're going to have a more moderate coefficient of friction. So in all of these cases, if all else was equal, we're not thinking about any other factors, we're just thinking about these three things right here, what we would see is that the ice would, if all else is equal, generate the lowest force of friction. This guy would generate the highest force of friction, and this would have an intermediate force of friction. So that kind of gets through the first factor, right? Our first factor that is sort of going into this is what materials are actually interacting, but it is not the only factor. The other factor that is going to matter is how hard do we shove these two surfaces into one another. Because the more we push these objects into one another, the more they are going to conform and get stuck on one another. Which means that heavier objects are generally going to have and be subjected to more friction. So if these surfaces were equal, we have two concrete things, these blocks are sitting here, we could think about what is the maximal static friction that it would take for each of these things to move. Well, in this case here, because this is going to end up pushing harder, or the force of gravity is going to push this thing harder into it, it will have a greater normal force than the 2 kilogram one over here. And we don't necessarily care about the force of gravity. I mean, we do care about the force of gravity. The force of gravity is why this thing is smushing down into it. But remember, what we care about is how much it actually smushes down into it, which is not just determined by the force of gravity. It's really equal to the normal force. Because if we go back to that scenario where I tie a rope to this guy and I pull up, and if we put some numbers here, we can see what's going on in this circumstance a little bit more easily. So we know force of gravity, mg, so 8 times 10, 80. So we have a force of gravity down of 80 newtons. And say this force of tension I pull up with 50 newtons. So in this circumstance here, the normal force would be 30 newtons. So what's going on in this case? Well, how hard is this object actually smushing into the surface? Well, it's only smushing into the surface with 30 newtons. Because sure, gravity pushed it with 80, but we pulled it up off with this rope. And because we pulled it up off with this rope, not all of that force that gravity generated goes to pushing down into this. Now if we go back to that original scenario, now we can understand why we really care about the normal force, which is obviously determined in part by the force of gravity, but ultimately this is the guy that we care about. We can see that this one here is going to basically smush harder and will therefore have a higher frictional force when we go and try and move this. And this one here is going to smoosh, I guess, lighter. It's kind of a weird thing to say, but we're going to say it. And this will have a lower frictional force. Now, I put both of these boxes in pink to try and indicate the fact that in either circumstance we're talking about the same exact materials, so you don't need to think about a change in the coefficient of friction in this particular circumstance. So hopefully you can sort of see how these different kind of features are sort of adding up and changing what's going on. Let's see, I'm going to skip that one. So then if we look at our force of friction, we know, or we should remember, that it's going to be equal to ma. That's not going to change. All forces, doesn't matter, will always be equal to ma. But it will also be equal to the normal force times the coefficient of either static or kinetic friction. This is just going to depend on whether it's moving. If it's moving, kinetic. If it's static, then the static one. And here we're seeing how each of these were impacting. So we said, hey, the more it smooshes, the higher the force. And we said, hey, the larger or the more like frictiony the surface is, the greater this will be. And this is the only factors that are going to matter. So let's say that we go back to one of our sort of like angle scenarios. We're going to look at this one again, and we're going to think about how we solved through it. So I'm gonna resolve this problem. It's going to end up basically looking the exact same. But in this circumstance, we're going to see something a little bit different, because what we want to do here is we want to solve for the coefficient of static friction. So in the last one, I said, hey, let's solve for the force of friction. But in this question, we're not going to solve for the force of friction. We're going to go a step further, and we're going to actually solve for the mu s. So in this circumstance, we are pulling right here at 20 newtons. This is going to be defined as being 60 degrees from some horizontal. Let's say that this guy ends up being a 10 kilogram box. So what do we know? Well, if we want the coefficient of static friction, the way that we would normally solve for this would be maybe finding the force of friction. And then if we know the normal force as well, we can come in and we can then isolate and solve for mu s. We need to understand all the different pieces and parts. So we're going to use our skills from the beginning of thinking about what types of things we have at play and putting everything here. So I know that we're on Earth, so we probably have gravity. So we have a force of gravity. And this is pushing into a surface. So we know that we have a normal force, like this here. Because this thing is stationary, but there would be supposed movement, right? It should move to the right, but it doesn't. There is a force of friction like this. And just like before, we're going to take our angled rope and we're going to break it into two different components. We have the force of tension x, so that's how much of this 20 newtons is actually pulling in the horizontal or the x direction. And then we also know that this, because we had it in our triangle right here, right? This was our 20 newtons. This would be the force of tension x. This is the force of tension y. We know that we also need to draw on here the force of tension y. So hopefully you can see how we put the pieces of this puzzle together and how we're also going to go about solving it. So we want to get force of friction. Well, this thing is stationary. It is not moving, right? It's not going anywhere, which tells us that this force of friction and this force of tension x, these are going to be identical, right? They will be equal to one another. So if we can find the force of tension x, we can go ahead and say, I have the force of friction. So I'm going to just come in here and just label that this is the force of tension x. Now, I need to find the normal force. And here, when we look at the situation, we should realize that it's not just going to be equal to the force of gravity because, right, it's how much we smush into the surface. And sure, we smush down with the 10 kilograms, but some of that is counteracted by the force of tension y. So what I'm sort of thinking is like, okay, great, the normal force will be equal to how much the gravity pushes into the ground, so the force of gravity, minus how much ever the force of tension y takes out of that. And then now we have our normal force, and it's just a matter of solving through these different pieces. So let's go ahead and figure out force of tension x. Again, this is our 30, 60, 90 triangle. So this guy right here, right, 2x, so this is x, so this is 10. So this guy is equal to 10 newtons. So now I'm gonna just come in and say, cool, 10 newtons. Awesome, that was really easy. And now let's see if we can figure out what the force of tension y is. This one is a little bit more annoying, because the force of tension y is going to be, or like on a 30, 60, 90 triangle, the one across from 60 is going to be equal to x square root 3. So x square root of 3 is not the most solvable, which is why if you've noticed when I've set these things up, I've set them up in such a way where you've basically been given a nice like, oh, just find x. We can estimate this relatively well. So we're going to go ahead and do this and just say that this guy right here is like 1.4. So what would I do? I would say x is 10, x times 1.4 will be about 14 newtons. So this guy right here is going to be 14 newtons. Fantastic. So now we have this, right? So now we have this guy right here. So we'll be able to plug in 14 newtons. How do we find Fg? Well, that's just equal to mass times acceleration. The mass is 10. The acceleration is gravity, which is also 10. So this is 100. So now we're going to come in here and we're going to put in 100 newtons. Let's just go ahead and take a little accounting, see, do we have everything? I think we do, right? So I just come in, I have everything that I need to find a normal force. Check. I have the force of gravity. I have the force of tension y subtracted from that. So if I do that math, I'll get this guy here. I have the force of friction because we know that it's equal to the force of tension x. Fantastic. Leaving just the mu s. And that's it, right? Now we're just going to go ahead and do this math. I hope I've picked math that's not completely horrible to do, but let's find out. So 100 minus 14. That should be 86. So now I have 86. Mu s is equal to 10. I will divide off by 86. I did not pick very good numbers. This is unitless, so we would be done. This would be 10 over 86. Hopefully the MCAT would pick better numbers. Alternatively, we could technically solve this. It's a little bit of a pain in the butt, or you could estimate this and say, okay, well, this is like 1 over 8.6. It's close to 1 over 9. 1 over 9 would be 0.11 repeating. It's a little bit bigger than that, and you could estimate. So you can see, you could go ahead and you could kind of estimate a lot of these things. But that's how we would go about solving this particular problem here. So it's just an extrapolation. It's just going a little bit further than the other problem that we solved before. Okay. Inclined planes. We're going to go ahead and chat about inclined planes, and we're doing it so late because you really need to know and understand friction and a lot of these different pieces to understand how inclined planes work. But to be honest with you, inclined planes are about as the same level or the same level of difficulty as the problem that we just did, because what I was doing there is I just pulled on my box with a rope, and so I have to split out that pull from the rope into its vectors. When it comes to an inclined plane, you're using the plane, and the plane is going to have to split out the vectors of gravity, because basically what happens is that gravity pushes the box down the slope, and it also pushes it into the incline. You'll see what I mean here in a moment, but honestly, these problems end up being remarkably similar. So if the first one made sense, hopefully inclined planes will be much, much easier to understand since we are a little bit clearer on essentially how all of this works. Okay, so when it comes to the inclined plane, like I was saying, you have this sort of triangle-y thing over here, and generally they're going to define an angle like this. So our box would be on this angle, and like I said, you have gravity which points straight down at the earth, like this here, but then the box is going to basically be moving like this. So the force pushes down, and it also pushes directly in. The normal, sitting on a surface, has to be 90 degrees, right? So 90 degrees, because we kind of talked about that. We call this right here the force perpendicular, and it's just coming from gravity, right? Because gravity is at this angle, it's sort of pushing straight down, but into this thing. So it's going to push it into it, but it's also going to push it down like this. And that will be the force parallel. And we're going to say that, yes, there is friction here. So the supposed movement should be down. So if we have a force of friction, it would go against that supposed movement, which would be pushing back up the ramp. I haven't specified whether this thing is moving or not, but don't worry about that too much. So this is what we're going to see in this circumstance right here. So how do we break this down? Well, we know that if we have the force of gravity, we have to be able to break it out vector-wise. So force of gravity comes straight down like this right here. So this guy will be Fg. And then we have the force of parallel, which comes like this. And then finally we have the force perpendicular, and that is basically forming your vector right here. I haven't done the best job because this should be a right triangle, and it does not look very much like a right triangle to me. So we're going to just pretend here for a moment that I did in fact draw a much better right triangle than I actually have. We'll make this our 90-degree angle right there. I can go through the whole trigonometry and geometry rules, but we're here to be doctors, not mathematicians or geometrists or whatever, right? And so I'm going to do a little bit of hand waving and just say that there is a relationship between this triangle and the triangle of the plane, such that the angle that is right here is going to end up being analogous or equal to this angle right here. at the bottom. Again, I'm doing some hand waving. It's for the sake of this being an MCAT video rather than deeply understanding the geometry of what's going on. What this means is that we want to understand how we generate these things. So we know that forces are generally going to be equal to ma. Now, because they're coming from gravity, this will be mg. But we know that it's not all of gravity. It's getting split into two different pieces, so not all of that gravity is going to end up going straight into it or straight down. Instead, we're going to end up using trigonometry, just sine and cosine. So we have so, ka, and we're going to forget about toa. So this is sine is opposite. So if I come to this angle right here, this is opposite over the hypotenuse. This is the hypotenuse component. So if you want to solve this out for the parallel, this will be F parallel is equal to mg sine theta. This guy is the adjacent. So as you can imagine, this will be perpendicular is equal to mg cosine theta. So if I'm looking at this sort of triangle that I have right here, we can now take what we have learned from it and we can just transfer it back over to this guy. So this will be mg sine theta, and then this guy right here, this first force perpendicular, will be equal to mg cosine theta. Awesome. So how do we actually solve a problem with this stuff, right? How do we take what we have and these different concepts and solve the problem? So let's say that in this scenario here, we want to know the mu k. So going back to that problem that we did before, it's going to be relatively similar. So we're going to solve mu k, and this box is traveling at a constant velocity down it. So constant velocity like this. Okay, first things first, what forces do we have? Right, so what forces do we have? Well, we know we're going to have gravity. So gravity would push this thing straight down. Since it's on an inclined plane, we can break that out. We have a force perpendicular and we have a force parallel. It's sitting on a surface, so we know we have a normal force, like this here. And lastly, we also know that we have a force of friction because there is movement, right? It's moving with constant velocity, so the force of friction will end up going here. Now, let's say that this box is a 30 kg box. How are we going to break down solving all of this? Well, it's really, really similar to what we had before. What do we know? We know that in order to solve for a mu k, we need to get the force of friction. In order to get the force of friction, we need to know the force parallel because there are no net forces, so these two things will end up being equal to one another. So we know that the force parallel will be equal to the force friction, will be equal to mu kn. So I'm going to just come in and rewrite this a little bit more simply. So force parallel will be equal to mu kn. And that's really just because solving for force parallel is really, really easy because as we just talked about, we have basically a formula, mg sine theta. So if I put in 30 times 10 times the sine of 45, I will end up getting force parallel. Now we need the normal force. So we know that again, because this box is not moving up or down anywhere, that the normal force and the force perpendicular will be equal to one another as well. So that piece is relatively easy to get to because it's just going to come from here. And again, this guy we have an equation for as well. So this will be mg cosine theta. So if I want to put this in, what do I have? I have 30 times 10 times sine 45 will be equal to mu kinetic times 30 times 10 times the cosine of 45. Well, the 30 and the 10 are on both sides. Those are just going to cancel each other out. So if I rearrange this, so I will have, I'm going to divide off the cosine 45. So I divide off the cosine 45, I get mu k is equal to sine 45 over cosine 45. Obviously, we'd have to do the math, right? I'm not doing the math in this particular circumstance. But what we're noticing is that you can actually shortcut this. If you have a situation where you have no net forces and you want to know and you want to solve for mu k in this circumstance, we have just proved to ourselves that we can simplify this down to a derived formula that can save you a bit of time. And that derived formula is basically right down here, but with the angle in it. And this would go for the stationary one as well. So here we would have the sine of whatever theta is over the cosine of theta. Again, remember, it's important that this is only going to work for a situation with no net forces. So if you have a scenario where there are no net forces, you can go ahead and you can use this one. Otherwise, you can solve it in the normal way if there happen to be net forces. Let's see. Okay, I'm going to go ahead and move on to the last law, Newton's last law, and this is going to be the third law, which basically just says that like if you push in an object, there's going to be an equal and opposite push from that object. This is a little bit confusing to me. It always was confusing. I was always sort of sitting there being like, how the heck, if you push on something and it pushes back equally, does anything move? Because it seems like those two net forces should cancel out with one another. But we have to be careful here, because Newton's law is actually kind of specific. What it's really saying is that when you push on some object, so this car pushes into this wall, right? This will be the force push. And that is happening on the wall. The wall pushes back on the car. So there's a force push like this. These two things don't add up vector-wise, because this guy right over here belongs to the wall. And this one right here belongs to the car. So that's why these things are not interacting with one another. Now, what's the consequences of these things here? Just let me put my... Okay. What's the consequences of these things here? Why does it matter? What's like the easiest way of sort of seeing this? I think the easiest way is going to be looking at kind of two different scenarios. So scenario one is going to be a scenario in which you have a rocket, right? So let's say you have this rocket right here, and it is sort of like sending off its thruster. The rest of the rocket is sort of like up there. How the heck does the rocket go anywhere if all it does is push a force down, right? So the force of the rocket is just down, which would make you think the rocket should go down. But what this rocket is doing is it's pushing on the air, and that air pushes back. So the force of the air on the rocket is actually what propels it forward, because there's no way that a downward force could cause a rocket to go skyrocketing into the air. Same thing too with this, if we're going to walk, right? So let's say that this is your leg. What do? You push into the ground like this. So this is your force push on the ground. Well, if you're pushing backwards, but you move forwards, how the heck did you move forwards? Well, what must happen is there must be something that's going to push you, and that's the ground. So the ground pushes back against you, and that causes you to move forward. I'm not exactly sure how the MCAT's going to test this. I think this would be mostly conceptual, so I think if you understand this kind of here, this should be enough to answer questions like this. So I'm not really going to go into much more detail, but hopefully Newton's third law makes a little bit more intuitive sense after understanding this here. Okay, so that's it for forces, right? So we've gone through lots of different practice problems. We've sort of seen the consequences of the different ones. We see how knowing the different types of forces ends up being really important. Let's go ahead and talk about torque. Torque is all about rotation. So let's just imagine you have this lever and it's fixed at the bottom here to something. So all it can do is rotate. You can sort of pull it down like this, or you could, push it like this direction here. So torque is going to be a measurement of when you do this, sort of like the magnitude of that particular rotation. So if I pull really hard, I'm going to get a great torque. If I push really hard, I will get a really big torque. If I don't push so hard, I'm going to get a smaller torque. So we're already seeing that first component that kind of impacts the torque, which is going to be the force. So here we can say that the greater our force, the greater the torque. We can also think about where we are pulling from. So let's just imagine you go and you try and pull this lever, and you're going to pull from right here at the bottom. You're going to pull like this. You're going to try and get it to rotate. This will be really, really hard. You're going to have to pull really, really hard to make this happen. But if you come out here and you do this now, and you pull, you will not have to pull nearly as hard to get this thing to rotate. So you can pull a lot more softly. And that's because when it comes to torque, the other thing that's going to impact it is, where is this force? Is this force really, really close, or is this force really, really far from a particular pivot point? So in this case, at the bottom. So that's the next piece that we can put here, would be the distance from the pivot. And like I said, if we are close to the pivot, then it's going to be really hard. We're going to get smaller torques. If we're going to have higher distances, then we're going to get greater torques. So let's say that we have this scenario here. We have a balance beam, and our pivot point is going to end up being right here. It's perfectly flat like this, right? It's perfectly flat just like this. And let's say that we're going to put one person on this balance beam right here, and we're going to put another balance beam, or another person on this balance beam right here. And in this circumstance, they're not going to rotate. What does this tell us? Well, if we remember from forces, right, we were thinking about these things as vectors. Torques also have vectors, but we think about this in terms of like clockwise or counterclockwise because it's rotation. So it's sort of like going in a circle rather than going, like left, right, up, down. So if this is the case, and we know that these people are going to weigh different amounts, right, then they must be balancing each other out, right? Because if we're not moving anywhere, then we're basically not having any net torques. We don't have something that is like causing this thing to go up one direction or causing this thing to go up the other direction. And if that's not the case, then it's just like a box. If you're pushing on one side of the box and equally as hard on the other, the box doesn't go anywhere. So if you try and get it to rotate one direction and equally hard try and get it to rotate the other direction at the same time, it won't go anywhere. So let's go ahead and think about this. Well, in this circumstance, what we can see is that this person is much closer to the pivot point. And this person over here is much further. So what can we state about these people's weights? Well, in order for them to be balanced, whatever torque they're generating must be equivalent. So in this case, this person must be heavier because they have to compensate for the fact that they're closer. Because if we go back, we remember that we said that, hey, like as we get a greater torque, they use this little symbol right here. One reason this would occur would be because you have a greater force. This person is heavier. So when gravity acts on them, they generate a larger gravitational force straight down. But we know that if we have a greater distance, then we would also get a greater torque. So over here, what we're going to see is that this person who is further, they have a greater torque because they have a greater distance from this thing. This person over here would therefore have a lesser torque because they have a lesser distance. So in order to compensate, the force must be equaling this out. So what does that tell us? That tells us in order for these two things to be equal, so for this to basically just be canceled out, the force over here must be greater and the force over here must be lighter, so this person must be heavier to compensate, and this person over here must be lighter to compensate for this here. So this is giving us a more conceptual understanding of how torque is working and the different factors that are coming into looking at it. But let's say that we want to quantify things. How do we actually go about doing this quantification? Well, one, we need to understand how do these variables connect? How do they actually make up the torque equation? Well, torque is basically going to be equal to the force times the distance from where you are. There's an angle component, but for a moment, we're just going to ignore the angle component. We're going to ignore the angle component for a sec because in most MCAT situations, you're going to be able to ignore it. Why? Because really we're just dealing with things at 90 degrees and that angle means that you just get all of it. We'll talk about the angle piece conceptually because I think that's how they're going to test a torque problem. So let's say that in this circumstance, what we have here is that we have a box. This box is going to be exerting a downward 5 Newton force. And this box over here is going to be exerting a downward 10 Newton force over here. This box is going to be 2 meters away from the pivot point. So now the question is, where should this box be placed to equal this out? Well, what do we know? This box right here would try and rotate this thing down like this. So we can just call this torque counterclockwise because it is going against the movement of a clock. And this box over here is trying to get this to rotate like this. And this is clockwise, so we'll go ahead and call that torque clockwise. Because this is not happening, these things are not rotating, it's just staying completely, stable. Not teeter-tottering, just right here. These two things must be equal, otherwise we would have some sort of net rotation. So torque counterclockwise must be equal to torque clockwise. So, hello. If this is the circumstance right here, then we know that, okay, great. This is going to be F times R. So if this is 5 newtons, we can say that this will be 5 newtons times r, which is going to be 2 meters. And this over here is 10 newtons, and then we can solve for the r, or the distance that this would be from the pivot point, where we should put this box down. So 5 times 2 is 10, is equal to 10r, divide off the 10, and we will get 1. So r should be 1. So we should take this box, wherever it is at right now, and shift it so that it will be now 1 meter away. Well, this is great, but with numbers this easy, we actually didn't need to go through this whole process. We could have just solved this out using proportions. So I want to show you how to do that now. So here's what we know. We know that as we have a greater distance, we will have a greater torque. And we know that as we have a greater force, we will also have a greater torque. So if I just come over here and I look at this circumstance, I can go ahead and label this and say, hey, you have the greater torque. So you have a higher torque value, yes, because you have a higher distance. But you over here are going to have a higher torque, backwards. I'm gonna start over, because I forgot that you don't get that. You get that, but you don't get this yet. So we have to just work with what we do have, which is the 5 and the 10. Okay, so here we know that this would have a lower torque because it has a lower force. And we know that this over here would have a higher torque because it has a higher force. Well, what do we know if we come down? We know that here, in order for this to still be the equal to what's over here, this one must have a greater distance, a greater r, and this must have a lower r. Well, what's the ratio of these two things? It's 5 to 10. So when I come from over here, this is a times 2 difference. So what does this tell us about the difference in the distances? It must be a times 2 difference. But in order for this to compensate, this needs to go down by times 2. So if this was 2, this would have to be 1. So there I'm just using the proportions to solve this. But again, if the proportions are easier, it's going to be a little bit more efficient. You're going to be able to solve it a bit faster. If, on the other hand, the proportions don't make sense, you can solve it the original way that I showed. Okay, now what I want to go ahead and do is I want to talk about angle, because I really omitted that from the equation. So when I wrote out my equation, it really should have looked something like this: RF sine theta. So first of all, what is this theta actually referring to? Well, if we go back to our lever scenario, everything that I have been describing so far has always been at a solid 90 degrees. So white is the pivot point. This was just like the little ball that you would hold onto to actually move this lever. So I was saying, hey, we're going to pull at a 90-degree angle like this. When you pull at a 90-degree angle, all of that force is going into causing this thing to rotate. To see why this is the case, I want to go ahead and look at basically two extreme examples here. So let's imagine that you are going to just grab onto the ball and you're going to just pull it straight up. You will never cause rotation, right? You will never, ever, ever, ever cause this thing to rotate by grabbing the top of this ball and pulling it straight up. What if, on the other hand, you push it straight down? Well, again, same thing. If you push straight into this lever, you're never, ever, ever going to cause rotation. So we can see that the angle of your force obviously matters because it depends on where this angle is. So if this is sort of your like zero torque, and this is your max torque value, you can begin to see how this will vary with the angle in comparison to this thing. So as you go from the angle all the way up here to 90, right, these torques will be increasing. And then as you go past this angle down to this other direction in terms of orient your force, your torques will begin to decrease. So for example, if we're looking at a graph and we're assuming that the force is the same, but we're looking at the torque, and over here we're at 0 degrees, and right in the middle we're at 90, and over here we're at 180 degrees, we should expect for the torque to be peak right here. And we should be expecting it to be at a minimum right here. So if we charted this out, this is what we would see. So basically, the sine theta value, as you are increasing this angle to 90, right? You're getting to 90, you're getting to 90, you're getting greater and greater torques because all of that is going into rotation. None of it is going to either pulling straight up or pushing straight in to this thing right over here. So that's what we're seeing with the angle. I think from an angle perspective, it's probably one of the few ways that the MCAT is likely to actually ask this. Obviously, you could see it in a problem. It seems a little bit less likely to me just from what I've seen and kind of what I know about generally how the MCAT asks. So for me, I would be thinking, know the sine theta or from a conceptual perspective, you're probably going to be dropping it in problems like this, because if we look at what is happening, your pivot point is here, this is oriented here, and this is at a 90-degree angle, and this is what you're most likely to see. Of course, you could have something like this. It just seems unlikely to me, and this is why I'm showing you the conceptual side of the torque and the angle. Okay, I want to go ahead and fast forward and look at a problem like this, because we've seen a couple of different problems, right? We've seen how these boxes are sort of getting balanced and whatever's going on, but now I want to look at a scenario, and this question is modeled after one from the AMC on one of the question packs, so not in the exams, no spoilers here, that has mass with the fulcrum. So before, we've been ignoring this fulcrum and just pretending like it doesn't matter, like it's just like whatever, right? It's just going to do whatever it is. But that's not always true, because this fulcrum right here, it can have mass, which means that if you were to, just for a second, get rid of these two things like this, and this was your pivot point, you have more mass on this side, and this thing would cause this to sort of rotate down, because it's more mass that's going to anchor around and pull like this. And over here, you have less mass, so it can't compensate, and it's going to kind of fly up like this. So if this is the case, right, we can't just ignore it, because we have some boxes attached to it. So if this is balanced, how do we actually come here and represent this thing's mass? Like, how do we figure out, when you have something with mass, what to do with it, where to put it? The easiest thing to do is to convert this thing, which has mass, to what we've been dealing with before, which is massless, because that's easier. But how do we convert it? Well, what we're going to do is we're going to find this thing's center of mass, and we're going to just pretend that all of the mass that this particular fulcrum has will be hung down like normal from the center of mass. So what do I mean by this? So right here, this guy would be the center of mass. Boom. Let's say that this is a 1 kilogram measuring stick, like this. So what I would do is I would say, great, if this is a 1 kilogram, whatever this happens to be, I hang this mass down right here, and I say that this is 1 kilogram, representing this guy. I can now solve this problem as though it was a normal torque one, and I don't have to think about the fact that the fulcrum itself has mass. So let's go ahead and do that. Let's go ahead and figure out what's solving. So let's say that this entire thing is completely balanced, so nothing is moving around. Let's throw some distances out here. So let's say that this guy is at 1 meter from the pivot point, which is right here. This one is going to be at 5 meters from the pivot point. This will be at 2 meters from the pivot point. This will be a 2 kilogram mass. And what we want to know is, what mass do we need to put over here in order to have this thing be balanced? Okay, so what's going on? So both of these are attempting to cause this thing to rotate down. Let's just call this torque 1, and we'll call this one torque 2. So in total, both of these things, torque 1 and torque 2, are attempting to cause this to go in the clockwise direction. So we can say that torque clockwise is equal to torque 1 plus torque 2. Now this guy, poor lonely guy over here, all alone, only working by himself for torque 3, so we can just say torque 3 is equal to torque counterclockwise. And so far, what we know is that all of these things, the torque counterclockwise and the torque clockwise, must be equal because there is no rotation. So I'm going to go ahead and write that up. So torque clockwise will be equal to torque counterclockwise. Now let's expand this out. So really, torque clockwise, that's going to be two things. That will be torque 1 and torque 2. So torque 1 plus torque 2 is equal to torque counterclockwise. Torque counterclockwise is just torque 3. Torque 1, this will be RF, but for 1, so its distance and its force. And this will be plus R and F, but for 2. So R1, F1, 2 equals to R3, F3. Now, we want a mass, we don't want a force. If I was to look at this force, the force is all coming from gravity, so mg. Great, it's all coming from mg, which means that there is a g in all of these things. It's just going to cancel. So if we want to solve directly for mass, we don't need to convert everything to forces, get that force, and then just remove the exact same acceleration that everything had to convert it into forces. We can just plug masses directly in, and that's what I'm going to go ahead and do. So I'm going to come in here, and I'm just going to get rid of all of these things. So this is actually going to be R1, M1, M2, and M3. Hopefully that sort of explanation there makes sense. If it doesn't, go ahead and leave me a comment and I can spend a little bit more time explaining why I'm able to do this. Now this is a plug and chug. We're just popping stuff in until we end up getting our answer out at the end. Okay, so R1, that's this guy, it's 1 meter. What's its mass? 1. So 1 times 1 is 1. This one's taken care of. That came from right here. This guy was 1. This guy's going to be 2. So what do we know? It's 5 meters away. Mass of 2. 5 times 2 is 10. Is equal to, now we're going to come over here. This is 2 meters away. And M3 is what we're solving for, because we don't know this yet. Now we're just doing math. 1 plus 10, 11. Should have picked better numbers. It's okay. This will be fine. So we'll have 11 is equal to 2 M3. We divide by 2. Divide by 2. 5.5 kilograms. So this guy right here should be 5.5 kilograms. Really, with a lot of these torque and the force body or the force problems, all they're doing is they are just adding extra steps. They're adding extra things that add up. If you can see the individual little steps and you're good at each of the little individual steps, then these problems really aren't so bad. It's going to be something where you're going to want to do quite a bit of practice. One of the recommendations I would have is, if you made it this far, you've gotten to the end of this video, go back through and try some of these problems maybe in a couple of days on your own. So there's been a lot in this video. The recording will be up. Try them on your own and then watch me walk through it. Can you do it, right? And go through the whole sequence. If you can start to go through the whole sequence, you can then start to, if you're struggling with this type of problem, jump up to an MCAT resource and say, okay, can I do this? Because if you can do the sequence of the problems that I put out here, you should be pretty good for probably not all, but almost all of the problems that the MCAT or even a third-party resource is potentially going to ask you, and then you can continue to learn from those. But yeah, that was what I had for today. I know it was a little bit long. It's a lot of physics, but hopefully you got something out of it. Hopefully it was a bit helpful. If you're still here, next week I'm going to be doing cars. So I'm going to do another one of these. I'm going to do a cars walkthrough. I did one a while ago. I've changed some things about how I think about cars, and so I'm going to be doing the exact same passage of my old walkthrough, but with my new thoughts, new ideas of what's going on. And then I'll be back to physics in the week after that. Yeah. I hope everybody has a good rest of their night and that all of your MCAT studying is going pretty well. Bye.